for the extended wait. But we're here. We're doing stuff. We are working on... Let's make sure that's not too loud. I have a feeling it's not anywhere close to being loud enough. There we go. Yeah, we just kind of want it in the background. Alright, so... I had things are getting easier with setting up the stream and stuff like that, but there's just like daily things that I'm not used to doing. But anyway, it doesn't matter. Point is that we're here. We got things going. Let's see here. We want this one. There we go. Okay, we're gonna watch this one. Again, I don't know if we'll watch the whole thing. We watched the whole thing last time, but we are going to watch it on 1.5 speed. And yeah, that's where we're at. That's what we're doing. Cool. If you're here watching me on ParaDiddlePete, I strongly advise you to go check out my other channel, which is just Tyler Lamond. That's where I have a lot of tech videos. The ParaDiddlePete one is more of gaming. It slowly was turning into tech, but I didn't want it to turn into tech. So then I just made another channel where I could put all my educational stuff, and that's what this is. I have tons of other videos there where I have labs and other past streams and then other videos that kind of talk about things and all this stuff. I try my hardest to make it make the most sense possible. Anyway, so if you like that stuff, please go over there and subscribe. All the good stuff. We're gonna go ahead. We're gonna get right into it. So.
Hi from Tokyo, Japan, and welcome to Jeremy's IT Lab. This video is about the Internet Protocol Suite, often called TCP/IP, the family of protocols that makes communication over the Internet and other networks possible. You've probably heard of some of these protocols: IP, TCP, UDP, HTTP, and so on. If you haven't heard of them, no problem. We'll cover many of these core protocols in this course. From the
Cool, just checking. Yep.
Suite of protocols, we can build what people usually call the TCP/IP model, a way of grouping protocols into layers based on the job they do. In this video, we're going to build that model step by step and use it as a simple map of who does what in a network. This is going to be one of the longest videos in the course, but there actually isn't a lot you have to memorize. We're covering a big picture framework about how networks work. Later, when you learn about things like IP addressing, routing and switching, TCP and UDP, and so on, you'll be able to drop each new topic into this framework and see where it fits and how it works with the others. There's also a lot of history and a bit of argument around different models, like the OSI model and various versions of the TCP/IP model. In this lesson, I'll give you a practical way to think about layers that will help you understand how networks actually operate. As you continue studying, you can add nuance and explore the debates if you're interested, but you don't need to solve those issues today. So relax, don't worry about memorizing every concept, and just focus on the big ideas and relationships between the layers. We'll revisit these concepts many times in later videos.
Dang, he's in a
All right, enough
hotel
talking,
in Tokyo?
let's get started. Let's begin with
nice
the importance of protocols and standards. A protocol is a set of rules defining how data should be communicated between devices over a network. Protocols are the languages that computers use to communicate. Just as someone who only speaks Chinese can't talk with someone who only speaks English, computers that speak different protocols can't exchange data.
Yeah, we talked about
Since the early days of computer networking, there have been several attempts to define the functions needed for computers to communicate with each other. These protocols were often developed by a specific vendor, such as IBM, to be used with their own products. With this proprietary approach, enabling communications between different vendors' products was difficult, if not impossible. For example, if we have an Apple iMac...
So I would like to just kind of point out here real quick. So you'll hear me say a lot of times that like everything is everything. And that's because like my approach to learning is that like the same way you're going to get good at math is the same way that you're going to get good at basketball, which is the same way you're going to get good at drums. And a lot of things that go on in life share the same core fundamentals. So for example, right here, he's talking about like this proprietary approach enabling communications between different vendors. It was difficult because everyone had their own things that were going on. Like he's about to talk about the Apple iMac was having a hard time to talk to the IBM server. They didn't have a common language to talk to. I think that's like the same exact thing that you see with to put it like very simple terms. Like you can't put a PlayStation 5 game and an Xbox One console and expect it to work. So anyway, just making small connections.
and an IBM server, each using its own proprietary protocols, the IBM server wouldn't be able to understand a request from the iMac. I'm just using modern devices here as a visual example, but this kind of problem was common in the early days of networking. To solve this issue, today's networks and the devices connected to them use standard vendor-neutral protocols and technologies. A standard is an agreed-upon specification that describes how a protocol or technology should work. When devices follow vendor-neutral standards, devices of all types can communicate with each other. For example, an Apple MacBook can access a website hosted on a Linux web server, and a PC running Windows can send an email that can be read on a smartphone running Android. As long as the devices follow the same standards, they can work together.
Okay, and that's the same way of how, like, there's a lot of translation layers that we have now that allow, like the way Steam works. Steam has something called Proton, and it's a translation layer that allows Linux to work with Windows. And then there's a lot of other translation layers that allow Androids to work with Windows and things like that, to work with ARM and things.
Together on the network. How did TCP/IP come about? Let's cover a bit of history. Early work on the computer networks that would evolve into today's internet began in the 1960s, mainly in the US. The US Department of Defense's ARPA, Advanced Research Projects Agency, funded ARPANET. It came online in 1969 to connect mainframes at universities and labs around the country. Here's a map showing ARPANET in the 1970s, connecting locations mostly around the east and west coasts of the country.
That's crazy.
ARPANET originally used a protocol called NCP, the Network Control Program. There was no TCP/IP in the early days. In 1974, Vint Cerf and Bob Kahn, two of the fathers of the modern internet, began developing TCP, Transmission Control Program, as an internet working protocol. TCP went through a few revisions and was later divided into two protocols that are still used today: Transmission Control Protocol, TCP, notice the name change from program to protocol, and Internet Protocol, IP.
It's not a program.
Together, these two protocols form the foundation of the protocol suite, widely known as TCP/IP today. And the ARPANET fully switched to use TCP/IP on January 1st, 1983. Over time, TCP/IP became dominant over other vendor proprietary solutions at the time because it was published as a set of open standards that any vendor could implement, and it could run over many different types of networks. And here we are, several decades later, still learning about TCP/IP. That's enough history. Now, who actually defines these standards? Most networking standards are created by independent standards organizations, not by a single vendor. Engineers from many different companies participate in the process. When it comes to networking, there are two organizations you should be aware of. The first one is the IEEE, the Institute of Electrical and Electronics Engineers. I mentioned the IEEE in the previous video when talking about Ethernet cables. The IEEE develops many of the technologies we use on local area networks, such as Ethernet, which is defined in the 802.3 set of standards. The IEEE also develops Wi-Fi, which is defined in the 802.11 standards.
Yeah, 802.11.
These standards include physical specifications like Ethernet cable types, Wi-Fi radio frequency, and how to transmit signals over the physical medium, whether a cable or a radio wave.
Those numbers.
But they also specify how to format messages to send them to another device over the medium. Both are important topics that we'll cover in this course. The second standards group is the IETF, the Internet Engineering Task Force. The IETF is an open community that defines many of the protocols used on the internet. A few examples are TCP, IP, UDP, HTTP, and DNS. If you don't know these protocols yet, don't worry, they're all in this course. The IETF publishes its standards in documents called RFCs, requests for comments, all of which are freely available on the internet.
Kind of like
the IEEE and IETF create the standards, and then vendors like Cisco implement them so that devices from different companies can work together. But there are many different standards and protocols, each solving a different part of the overall communication problem. To make sense of them, it helps to group their jobs into layers, making a layered model. So let's look at that layered model. Networks do a lot of different jobs when they move data from one computer to another. Things like the physical transmission of signals, local delivery of messages on a LAN, routing traffic between networks, maintaining end-to-end conversations, and the applications themselves. A model lets us group related jobs into layers. Each layer has a specific role, and each layer uses the services of the layer below and provides services to the layer above. We'll come back to this idea later. Protocols live mostly at one layer. I say mostly because sometimes the lines are blurred and it's hard to categorize a protocol.
See, that's the part that I have.
Some examples of protocols that we'll look at later are IP, TCP, and HTTP. Together, they form a stack of protocols that work as a team, often called the network stack. Here's an example of a protocol stack from RFC 791, which defines IP, the Internet Protocol. It was published in 1981, but this is...
See, okay, this is where I struggle with too, is that at layer 1, it says that we have IP, TCP, HTTPS, but according to the iOS model, the other one that has 7 layers, this is layer 7, not layer 1. So are they like flipped? Which is fine. I just need to know so that way it's
still the current standard we use today. If you're curious, do a Google search for RFC 791. As I said in the previous slide, RFCs are freely available online, although they can be quite dense reading. You don't need to read them for the CCNA. We can divide this stack into a few layers like this. At the top, we have the application layer, with protocols like Telnet, FTP, and TFTP. I won't define these protocols now, but they're all covered in this course. Then below it, we have the transport layer, with protocols like TCP and UDP. Below that is the internet layer. Here, internet doesn't just mean the internet, the public internet you're probably using to watch this video. It refers to an internetwork, multiple networks connected together. That's the real job of this layer. This is where we find IP, which has two versions in use today, IP version 4 and IP version 6, both important CCNA topics.
Okay.
Finally, we have the link layer, including local network protocols like Ethernet and Wi-Fi. Each of these layers and the protocols in them plays a different role in the network. This is the TCP IP model, at least one version of it. The model is a description, not a law. For example, different textbooks and courses use slightly different models, some with 4 layers, some with 5 layers, and some with more. In this course, I'll use a 5-layer model that builds on this one. Before talking about networks specifically, let's use an analogy for this layered approach, sending a letter to a friend via the post. I don't use analogies like this often because they can cause misunderstandings if you take them too seriously, but I think this one is helpful. On the left, you're in your house, and on the right, Bob and his wife are at their house, with a couple of post offices between connected by roads. You write a letter, which is addressed to Bob. You then put the letter in an envelope addressed to Bob's house. Bob's house is a bit far from where you live, so instead of driving directly to his house, you deliver the envelope in your car to post office A, like this. Notice the 3 different destinations. Your car is going to post office A. The envelope inside your car is going to Bob's house, and the letter inside the envelope is going to Bob himself.
And those post offices
Post office A
routers.
then moves the envelope to a truck and delivers it to post office B, like this.
And the road is
The truck's destination is post office B, but the envelope and letter inside keep their original destinations.
Man,
Then post office B moves the envelope to a new truck and delivers it to Bob's house, like this. Once again, this truck has a different destination from the previous truck, Bob's house. The envelope and letter inside still have their original destinations. The envelope is now delivered to Bob's house, opened, and the letter addressed to Bob is read by him. So in this simple mail system, different parts care about different things. The message itself, who should read it, which house it goes to, and how it moves along the route. We can turn those roles into a layered model, and then compare that model to how TCP IP works. So let's build that model. Don't worry about remembering this model or the names of the layers, it's just an analogy for now. At the top, we have a content layer, the text of the letter, what you actually want to say. I'll call the next layer the recipient layer, the to Bob part, indicating who inside the house should read the letter. Below that is the address layer, which is the destination address of the house where that person lives. Next is the local delivery layer, which handles moving the envelope to the next stop on the path using cars and trucks, from your house to post office A, then post office B, then Bob's house. With these 4 roles, we already have a simple 4-layer model, similar to the TCP IP stack I showed before. But we can add one more layer at the bottom. I'll call it the infrastructure layer, the roads and other paths that the vehicles travel on. But really, these bottom 2 layers are related and always work together.
Yes.
If traveling over ground, local delivery uses a car or truck. If traveling in the air, local delivery uses an airplane. If traveling by water, local delivery uses a ship.
So what he did is that we have the local delivery layer, which is delivers to the next stop. So that's this. And he went a step lower, talking about the infrastructure of what is actually the transporter, what's actually transporting these things to go. And they're the same layer. He just kind of divided it inside of itself. So that way we can determine if it's Wi-Fi or if it's a LAN, things like that.
And often the letter will travel over multiple kinds of paths in its journey.
Exactly.
Ground, then air, then ground again, for example. You can either think of these 2 bottom layers as one combined delivery layer, or split them into 2 layers. And that's why some networking models use 4 layers, and some use 5. One of the benefits of a layered system like this is how the layers work together, but remain separate. Each layer has its own job. They work together to deliver the message, but each one focuses on its own task. The content layer focuses on the actual contents of the letter, and that doesn't change throughout the journey. The recipient layer focuses on the individual person who should receive the letter, and also remains the same from start to finish. Likewise, the address layer focuses on the address of the house or building to which the letter should be delivered, and that stays the same as well. The local delivery layer focuses on getting the letter to the next stop in the route, post office A, then post office B, and finally Bob's house. The infrastructure layer is the system of roads and mail trucks that the delivery process relies on. What happens inside one layer doesn't change the job of the other layers. For example, changing the content of the letter doesn't change the delivery steps, and changing the delivery path doesn't affect the letter itself. When you're writing the letter to Bob, you don't have to...
That's true. Work together message, but each one focuses on their own task. Right, but like, what if it loses packets in each layer? It's gonna determine, that might halter it. You know what I'm saying? I don't know. Maybe I'm getting too deep. Maybe I'm going too far too fast.
To think about how the postal service will go about delivering it. Of course, that doesn't mean the layers are entirely independent. For example, if you address the letter to somewhere overseas, that will influence how it's delivered. But that's not your concern as you write the letter. This separation of layers is true in our mail system example here, and it's true of networks as well. Now let's replace letters with data and roads with networks, and build the 5-layer TCP IP model we'll actually use. Here are the 5 layers of our mail system. Let's map them to the TCP IP model. The content layer is equivalent to the TCP IP application layer. The recipient layer maps to the transport layer. The address layer matches the internet layer. These are the same names I showed before for the TCP IP model, but I'm going to use a different name next. The local delivery layer matches what I'll call the local network layer. This is the layer used for delivering messages within a LAN, a local area network. There are a few different names for this layer, but I'll go with local network.
Okay.
And finally, the infrastructure layer is equivalent to the physical layer. At this point, these names probably don't mean much to you. So next, we'll see how they actually work in a real network between a client and a server. Here is a simple network I'll use to demonstrate. You've seen these icons before.
Okay,
on the left, we have PC1, a client that will send a request to server 1, the server on the right. Between them are two routers, R1 and R2, and two switches. Switch 1 between PC1 and R1, and switch 2 between R2 and server 1. PC1 is running a web client application, in other words, a web browser such as Chrome. Server 1 is running a couple of processes, a web server and a file server. PC1's user wants to access a web page hosted on server 1, so the web client on PC1, let's say it's Chrome, needs to send a request to the web server on server 1. That's the role of the application layer. It includes protocols for communication between application processes, and is responsible for creating and interpreting the data. But there's a problem. There are multiple processes running on server 1, a web server process and a file server process, and possibly more. So how can PC1 ensure that its request reaches the correct process on server 1? That's the role of the transport layer. Each process on server 1 has an associated transport port number, 80 for the web server and 21 for the file server. Don't worry about the exact numbers for now, that's for later in the course. The important point is that to send a message to the web server, PC1 addresses it to port 80. Don't be confused by the name port. These aren't physical ports like we looked at in the previous lecture. Here, a port is just a number used to identify a process running on a host.
Okay.
The role of the transport layer is to provide end-to-end communication between application processes, such as the web browser on PC1 and the web server on server 1, using port numbers. But we still have a problem. Even if the message is addressed to the correct port on server 1,
I still struggle with figuring out understanding ports because there are some ports that are like, they never change. They're always that. Like, if you wanted to, you could look up and see what port Xbox was, what port YouTube is. And it's like, okay, so then how does the port and the port number, how does that fit with the IP address? How does that work?
we still have to make sure the message reaches server 1 in the first place. Server 1 has an IP address for that purpose. For example, let's say its IP address is 10.1.1.1. Again, don't worry about the format of the address itself yet. That's a topic for another video. By addressing its message to server 1's IP address, PC1 tells the routers in the path which host the message should be delivered to. That's the role of the internet layer. It provides end-to-end communication between hosts, from the source host to the destination host, using IP addresses and routers. When you think of the internet layer, think IP addresses and routers. And host, by the way, just means a device connected to the network that can send and receive data, such as PC1 and server 1. So we're getting close to achieving our goal of getting PC1's request to server 1, but we're not quite there yet. There are several devices between PC1 and server 1, and we need to make sure the message is properly passed along between them.
So far.
That's the role of the local network layer. Using protocols at this layer, such as Ethernet, each device sends the message to the next device on the local network. PC1 to R1 via switch 1, R1 forwards the message to R2, and finally, R2 forwards the message to server 1 via switch 2. The local network layer provides hop-to-hop delivery within a local network using MAC addresses and switches. I'll explain the term hop-to-hop more in a bit, and MAC addresses are a topic for another video. Looking at this diagram, you might wonder about the role of the switches. They connect devices in LAN and pass messages between them. We'll look at how that works in detail in future videos. Okay, and last but not least, we have the physical layer. All of these cables connecting the devices, and the transceivers on the devices that transmit and receive signals. The physical layer sends bits as electrical, optical, or radio signals over the physical medium. Electrical signals over copper UTP cables, optical signals over fiber optic cables, and radio signals over wireless Wi-Fi connections. We've covered the role of each layer, but now let's go from the bottom up, from the physical layer to the application layer, and look at a few more details. The physical layer, also called layer 1, is responsible for sending and receiving bits as electrical, optical, or radio signals.
So that's the other thing that I've noticed too, is difference between this and the ISO, is that, well, maybe it was just his approach of like how he explained it, which was good, by the way. He explained it in the terms of where it was going first, or what we were trying to do. Well, okay, so I'm the client, and then I went through all of these steps to get here. So if I'm the client, I go through all these steps to get this, and then the web server goes through all of these steps to get back to me. Okay, that makes sense.
The physical layer, also called layer 1, is responsible for sending and receiving bits as electrical, optical, or radio signals over the medium. It defines things like cables, connectors, signal levels, and link speeds, all of the physical aspects of communication. Examples include copper UTP and fiber optic cables, Wi-Fi radios and antennas, and network interface cards, also called NICs. Here are a few examples. UTP ports and a cable on the left, fiber optic in the middle, and an image of a NIC on the right. Each network interface has a NIC like this inside of the device. The physical aspects of transmitting data are very complex, involving a lot of electrical or optical engineering. Fortunately, network engineers typically don't have to know the low-level details of how it all works. So that's the physical layer, layer 1 of our TCP IP model. In some models, this layer is combined with the next layer, but I think it's useful to differentiate between the physical concerns like these and the logical aspects of layer 2. Next, we have the local network layer, layer 2. This layer provides hop-to-hop delivery of messages on a local network. So what exactly is a hop? A hop is one step along the path between two devices, from one router or host to the next router or host in the path.
Yep.
When PC1 sends a message to server 1, how many hops are there? The first hop is from PC1 to R1. The second hop is from R1 to R2, and the third hop is from R2 to server.
Oh, so we don't count a switch as a hop? Why? Is it because the switch mainly deals with MAC addresses, and it usually can be done with... That one, maybe I'm still sleepy, but that one kind of breaks my mind for a moment.
Server 1, so 3 hops in total. The switches don't count as hops. A switch just extends the local network, allowing multiple devices to connect. To keep the diagram simple, I only show one host connected to each of the switches, but there could be many more connected like this. The switch allows them all to connect to the same local area network. We'll look at switches and LANs in detail in later videos, so don't worry about them for now.
So
Layer 2 uses MAC, Media Access Control addresses, to identify interfaces. Each device connected to a LAN has a unique MAC address for that specific interface. Since R1 and R2 have multiple interfaces connected to the network, let's add some simple interface labels. G1 for Gigabit Ethernet 1, and G2 for Gigabit Ethernet 2, meaning these interfaces operate at a speed of 1 gigabit per second. PC1 sends the message to the MAC address of R1's G1 interface, its NIC. That's the interface that will receive PC1's message. R1 sends the message to the MAC address of R2's G1 interface. And R2 sends the message to the MAC address of server 1's interface. Once again, we'll cover MAC addresses in another video when we learn about switches. The key protocols at this layer that you should know for the CCNA are Ethernet and Wi-Fi. Others exist, of course, but these are by far the most commonly used layer 2 protocols today. Next up, we have the internet layer, which is layer 3 of our model. This layer provides end-to-end delivery between hosts across multiple networks. We call it end-to-end because it focuses on getting the message from the source host all the way to the final destination host, instead of worrying about each individual hop in the middle. Remember, internet means inter-network, between networks. It uses IP addresses to identify hosts in the network, kind of like a home address. In our example, server 1 has the IP address 10.1.1.1. So when PC1 sends a message to server 1, it addresses the message to server 1's IP address. Routers operate mainly at this layer, using the message's destination address to forward the message toward its final destination host. There are a few protocols at this layer that you'll learn about for the CCNA. IP, both version 4 and version 6, and ICMP, the Internet Control Message Protocol.
I wonder, could I put my entire house and everything just solely on IPv6? And if I did, what would happen? I'm going to go on a limb here and say probably nothing.
Next is layer 4, the transport layer. This layer provides end-to-end communication between application processes. And why is that needed? Well, in our example, our server, server 1, provides multiple services. It's running a web server and a file server, and perhaps other services.
I don't know.
If server 1 receives a message, it needs a way to know which of these services should receive the message. This can also be called process-to-process or service-to-service communication. This layer uses port numbers to identify the processes on each host, such as port 80 for the web server and port 21 for the file server. So when the web client on PC1 wants to send a request to the web server running on server 1, it addresses the message to port 80. And if PC1 wanted to access the file server instead, it would address its message to port 21. The transport layer allows hosts to differentiate between these different streams of data. Layer 4 runs mainly on the communicating hosts, PC1 and server 1. Routers normally operate based on IP, layer 3, not on transport layer information. There are exceptions, of course, but that's a topic for later in the course.
What I get confused with ports is when it gets messing with NAT and PAT, because in my mind it makes sense, like, okay, so this is the server and this is its IP address, and then inside the server we have these things. It's like, okay, so is that equivalent to like PAT or NAT or dynamic NAT, whatever you want to call it? Is that the equivalent of that? Because like I have one router in my house, but I have, I don't know, 7 devices that are connected to that. And they're all sharing the same public IP address. And they're all assigned not a port address, but they're all assigned a number. So I don't know.
4 is primarily a conversation between the two communicating hosts. There are a few protocols used at this layer. The two most prominent are UDP, User Datagram Protocol, and TCP, Transmission Control Protocol. They both offer some different features, and we'll cover them in this course. Finally, we have layer 5, the application layer. This is where network communications meet applications. Small side note, this layer is usually called layer 7. I'll explain why later when we talk about another model, the OSI model. The application layer defines how application processes format, send, and interpret data. So when Chrome on PC 1 sends a request to the web server process on server 1, it uses an application layer protocol, such as HTTP, to format and send the message. And that same protocol tells the web server how to interpret the message it receives. Protocols at this layer define message formats and rules for specific tasks. Here are a few examples. For browsing web pages, we use HTTP, or more often, its secure version, HTTPS. For file transfers, we can use FTP, TFTP, or another similar protocol. And email uses its own protocols too. Don't worry about these specific protocols or their names at this point. Right now, we're just talking big concepts. Network infrastructure devices like routers and switches typically don't care about application layer details. This is too high level for them. They just move messages across the network. Only the communicating hosts, PC1 and server 1 in this case, actually look at and interpret the application layer data. Now that we've seen what each layer does, how does a single message actually include all of this information at once? Let's see how the layers combine into a stack and how data moves through them using encapsulation and de-encapsulation.
Yes.
To show how encapsulation and de-encapsulation work, let's simplify the network, making it a direct connection between PC1 and server 1. First, the application layer prepares the data to be sent over the network. For example, an HTTP request that Chrome on PC1 sends to a web server running on server 1. As the message moves down the stack, each layer encapsulates the data with a header that contains the information needed by that layer. For example, the source and destination addresses, layer 4 port numbers, layer 3 IP addresses, and layer 2 MAC addresses, among other information. So first, the transport layer encapsulates the data with its header, the layer 4 header, with source and
just so you know, these all are like capsules, and inside of each capsule are packets of data. And those packets of data are just nothing but bytes and bits that are arranged in a certain order so that way it can be translated later. And as we move down, we're going to get more encapsulations. We're going to get more packets that is just going to make this long thread of data. Because if you remember in the last video we talked about it, data doesn't move like this. Data moves like this in a wire. So it can only go so big. Think of it like a car. Like, sure, you can put some stuff on your car, but you're not going to put like layers of stuff on your car of people walk so that way you can drive like that. Or like a train, it's going to just elongate like that. And that's what's happening with this, with the encapsulation and decapsulation. Encapsulation means that it's making more. Decapsulation means that it's unpacking it.
Destination port numbers and other information. Then the internet layer adds its header with source and destination IP addresses. Then layer 2 encapsulates the data with both a header and a trailer. The trailer is used by the receiving device to check for transmission errors. We'll look at this in more detail in a later video about Ethernet. Finally, the physical layer transmits the bits as signals over the physical medium, which is an Ethernet cable in this case. I'm showing the message in order from left to right here. So the layer 2 header is transmitted first, and the layer 2 trailer is transmitted last. So that was the encapsulation process. Now let's look at decapsulation. The receiving device receives the message as a stream of bits at layer 1. Layer 1 simply passes those bits up to the next layer. Now it's up to the other layers to interpret those bits. The device examines the information in the layer 2 header and trailer and then removes them. This is called decapsulation, or sometimes de-encapsulation. The decapsulation process continues up the stack. So layer 3 examines and removes the layer 3 header. Then layer 4 examines and removes the layer 4 header, and the data is delivered to the application layer. Now the application processes the data and, if needed, generates a response that goes back down the stack and is then transmitted back to PC1. So that's the decapsulation process, which is basically the...
And this literally all happens within like a fraction of a second. Isn't that insane? Isn't that so amazing? And just so you know, like, this doesn't change whether you're on the client side, or sorry, the server side or the client side. It is always doing this. It is always going down and back up, and then down and back up. It is always doing that. I had a hard time understanding that, and then when I realized that, that made a lot of sense.
Encapsulation process in reverse. Each device has its own network stack. A message from PC1 goes down its stack, crosses the wire, and then goes up server 1 stack, where the application layer processes it. The response does the same thing in the opposite direction. It goes down server 1 stack, is sent over the wire to PC1, and then goes up PC1 stack, where the data is interpreted by the application.
Yep.
In a real network, there are switches, routers, and other devices between the hosts. That adds more steps to the delivery process, just like the mail system example, where the letter is moved between cars and trucks. But the overall flow is still the same. Each host sends a message down its stack, across the network, and up the other host stack. We'll look at how those intermediate devices, the routers and switches, handle messages in later videos. Now that we've seen how encapsulation and decapsulation work, let's look at what to call these messages. At each stage in the encapsulation and decapsulation process, there is a name given to the message. The combination of data and a layer 4 header is called a segment when using TCP, or a datagram when using UDP. Remember that point. TCP creates segments, and UDP creates datagrams. This difference has to do with how TCP and UDP treat the data, but we don't...
If I remember correct, TCP checks, UDP doesn't check. So like when you're getting a Word file or Word document, it's TCP, and when you're playing a video game or watching Netflix or something, it's UDP. Which I learned some cool things about Netflix, about how you can't record your screen on your phone when you're watching Netflix. Very interesting, because everything has layers in a protocol, and going to your screen is no different.
Don't need those details yet. The combination of a segment or datagram and a layer 3 header is called a packet. Packet is the most common term we use when talking about messages being sent over a network, but strictly speaking, it refers to the message at this stage in the process. Finally, the combination of a packet and a layer 2 header and trailer is called a frame. This is what is actually sent over the wire. You'll never see a packet, segment, or datagram traveling over the wire itself.
Okay.
They are always sent inside a frame.
So they're different sizes of stuff. So we have the header and the data. So the data is nothing but data. And then the header and data is either a segment or a datagram, depending on whether it's using TCP or UDP. And that's part of the...
From Indonesia.
Whoa, man, that's crazy. That's crazy. That's crazy. Well, hello from Texas. Okay. And then we have packets from header. That's where we get the header. And then, or sorry, not the header. That's where we get the crap. What was it? What I really need is this. What timestamp am I at right now? 32. So application then becomes a data fragment. Then it becomes a packet, and then it becomes a frame.
Combination of a segment or datagram and a layer 3 header is called a packet. Packet is the most common term we use when talking about messages being sent over a network, but strictly speaking, it refers to the message at this stage in the process. Finally, the combination of a packet and a layer 2 header and trailer is called a frame. This is what is actually sent over the wire. You'll never see a packet, segment, or datagram traveling over the wire itself. They are always sent inside a frame. We can also use alternative names to describe the message at each stage, using the term Protocol Data Unit, or PDU. A segment or datagram is a layer 4 PDU, or L4 PDU. A packet is a layer 3 PDU, or L3 PDU.
Acronyms.
And a frame is a layer 2 PDU, or L2 PDU. Both names are common, so I recommend knowing both. And there's one more important term to learn. The contents of each PDU, that is everything encapsulated by the layer's header and trailer, are called the payload. So at layer 4, a segment or...
Wait, what was that? Contents of each PDU, and PDU stands for Protocol Data Unit. Everything encapsulated by the layer's header and trailer is also called a payload. So this is also called a payload. So a segment or a datagram payload. Oh no, just in general, these are all called payloads. Is the application data.
Or datagram's payload is the application data itself. At layer 3, a packet's payload is a segment or datagram, including the layer 4 header and the data. And at layer 2, a frame's payload is a packet, including the layer 3 and layer 4 headers and the data. Just remember that the payload is what's inside the PDU, not including that layer's header or trailer. Finally, let's talk about how these layers interact with each other. I've replaced the generic layer names with examples of common protocols. Also note the distinction between layer 2 Ethernet, which defines MAC addressing and frames, and Ethernet at the physical layer, which defines the signaling and physical media. Each layer in the stack provides a service to the layer above it and is serviced by the layer below it. This is called adjacent layer interaction. For example, layer 4 provides a service to layer 5 by delivering data to the correct application using port numbers. Layer 3 provides a service to layer 4 by delivering segments and datagrams to the correct destination host using IP addresses. Layer 2 provides a service to layer 3 by delivering packets to the next hop using MAC addresses. And layer 1 provides a service to layer 2 by sending and receiving the frame's bits as electrical, optical, or radio signals over the physical medium. Each layer relies on the layer below it to do its job. There's also a related concept. Each layer communicates with the same layer on other devices, and this is called same layer interaction. For example, the application layer on one host sends data to the application layer on the other host. A segment or datagram is addressed to the layer 4 port number of the correct application on the destination host. A packet is addressed to the layer 3 IP address of the destination host. A frame is addressed to the layer 2 MAC address of the next hop. And signals sent out of a physical port are received by a physical port on the connected device. This layered cooperation within each device and between devices is what makes network communication possible. Just like in our mail system example, the separation of layers is key to how networks work. Each layer has its own job and provides a specific service to the layers above. Because the layers are modular, we can swap protocols at one layer without changing the others. For example, instead of a web page exchange using HTTP and TCP, maybe it's a file exchange using TFTP, Trivial File Transfer Protocol, over UDP. The lower layers in the stack can use IP and Ethernet without worrying about the details of what the upper layers are doing. And if instead of a wired Ethernet connection, it's a wireless Wi-Fi connection, layers 1 and 2 can change to Wi-Fi without affecting the upper layers. As long as each layer keeps its contract with the layers above and below, we can improve or replace protocols at different layers without redesigning everything. That flexibility is one of the main benefits of a layered model. Now that we've built this 5-layer TCP IP model, let's see how it compares to other models you'll see in other courses and books, like the OSI model. You might have heard of the OSI model before. If you've studied IT before, you almost certainly have. As I said at the beginning of this video, TCP IP development started in the 1970s with work on ARPANET and the early TCP IP specifications. But in the late 1970s and 1980s, the International Organization for Standardization, the ISO, designed a 7-layer model called OSI, Open Systems Interconnection, and a matching protocol suite. The goal was to create international vendor-neutral networking standards that could unify existing proprietary stacks and potentially replace TCP IP as the vendor-neutral choice. Here is that model, with 7 layers from top to bottom: application, presentation, session, transport, network, data link, and physical. Governments, including the US, promoted OSI as the preferred or recommended stack for new deployments.
I kept calling the ISO. I'm dyslexic, sorry guys. OSI.
And for a while, many people thought OSI was the future. But OSI protocols ended up being developed too late and were too complex, and they never gained the same level of deployment as TCP IP. I wasn't around at the time, but my understanding is that this was largely due to the bureaucratic nature of the approach to developing OSI and its protocol stack. The process was very top-down. Committees designed the protocols in detail, and vendors were expected to implement them exactly as specified. TCP IP used a more bottom-up approach. In the end, TCP IP won in the real world, although some OSI technologies are still used. Today, almost all networks use the TCP IP protocol stack, but the 7-layer OSI model survives as a reference and teaching model, and as a common way to talk about layers. Actually, most networking resources use a 5-layer model, like the one I covered in this video, but with names borrowed from the OSI model. Here is that 5-layer model. I foreshadowed this earlier in the video, but this is why the TCP IP application layer is often called layer 7, because the application layer is layer 7 of the OSI model. I've also highlighted the 2 layer names that are different from the model I introduced. Layer 3 is called the network layer, and layer 2 is called the data link layer.
Which makes sense. Network layer would be IP layer, and then data link would be MAC. Okay, which would be switches. So layer 2 is like switch, and then layer 3 is routers, which is why we have layer 3 switches. Which, yes, okay.
And to make things even more confusing, here's a selection from Wikipedia of different models proposed by various authors. Here we have the 4-layer TCP IP model I showed at the beginning of this video. Here is the 7-layer OSI model, and the adapted 5-layer model I just showed in the previous slide.
So they're all doing the same thing. They're all basically doing the same thing. It's just a matter of how they labeled it and what they're doing and where they're doing it at. Like, it's all doing the same thing. Some of them didn't even label the software, or they named it hardware instead.
When you see all of these variations, you might wonder which model and which names you should actually learn. Of course, I recommend the 5-layer model I presented in this video, because I think its names best match the job of each layer. But this 5-layer model shown here is probably the most common in books and other resources. The only differences from my model are that layer 3 is called the network layer, and layer 2 is called the data link layer. In the end, it's not that important.
See, because what's the difference between this one that's the TCP/IP protocol suite or 5-layer internet model by this, whatever that is? TCP model, okay, the same host to host or transport, same network, internet, same data link, network access, same physical. So there's like next to no difference between these two. So it's really the core concept of understanding what the process of what's happening and how you feel like those things should be grouped or named. This is education bullshit right here. Like, where in education they'll come up with a name for something, and then they'll, like, a year later they'll be like, well, we don't really like the word negative and positive chart. We're gonna make a positive delta chart, because delta means change. Okay, baby. Okay, buddy. Like, what are we doing? So really, it's just the concept of what's happening in each one of these things.
In practice, people usually just refer to layer 2 and layer 3, and you won't be quizzed about layer names on the CCNA exam. Before wrapping up, let's review the key concepts from this video. I won't explain everything again here. I'll just point out what you should focus on as you review. The first is, of course, the TCP IP model itself. You should know the general purpose of each of these layers. I also recommend knowing these more commonly used names borrowed from the OSI model. It's also important to understand the encapsulation and decapsulation processes. In encapsulation, the sending host adds headers and a trailer to the data to prepare it for transmission over the physical medium. In decapsulation, the receiving host removes the headers and trailer layer by layer until it gets to the data inside. You should also know the names of the different PDUs, protocol data units. The layer 4 PDU is a segment when using TCP and a datagram when using UDP.
I wonder what the lore is about knowing the segment is TCP and then the datagram is UDP. For some reason, that makes a lot of sense in my brain, and I have no idea why that makes sense. I don't know why TCP, which checks, would be segment, and then datagram, which is UDP, which doesn't check. Anyway.
The layer 3 PDU is called a packet, and the layer 2 PDU is called a frame. The frame is what is actually transmitted over the physical medium. And finally, you should understand adjacent layer interaction and same layer interaction. These concepts describe how the different layers work together within each host and with their counterparts on other devices to achieve communication between applications over a network. That's all for this video.
Yeah, it's good thing.
Because the packet tracer version itself is different.
Interesting. Thanks for the heads up.
The TCP IP model. By now, you should have a mental picture of the 5 layers, what each one is responsible for, and how they work together using encapsulation and decapsulation. You don't need to remember every example or historical detail. The important thing is that you know the layers, their general roles, and the idea of PDUs and layer interaction. We'll keep coming back to this model throughout the course. You'll hear the terms layer 1, layer 2, layer 3, and so on many times. As we dive into topics like Ethernet, IP addressing, TCP, and routing, you'll be able to place each new concept at the right layer and see how it fits into the bigger picture.
Next.
Just remember, this is a model, not a law. Real protocols don't always fit neatly into a single layer, and that's okay. The model is just a tool to help you think about what's happening in the network. If you'd like a structured companion to these videos, I've also written 2 books, Acing the CCNA Exam, Volume 1 and Volume 2. They go into more detail than I can fit in the videos and include hundreds of diagrams and practice questions. I honestly think they're my best work when it comes to teaching the CCNA. If you're interested, you can find them on Amazon or use the links in the description to get them directly from the publisher. Thanks for watching. Before we wrap up, I want to say a quick thank you to the channel members whose names you see on screen. Your monthly support helps me keep making these videos and keep this content free for everyone on YouTube. I really appreciate it. Thank you for your support. If the video was helpful and you want to support me, click the join button under the video. Thanks again.
Nice. Okay, cool. This right here is just GPT, so we can ask questions. Okay, we're gonna get into the packet tracer. That's what we're gonna do next. And then we're gonna follow along. Yeah, there we go. Okay, we got some. What? I don't know what's happening. Okay, we're gonna move that right here. Actually, we'll move this over so that we can put this more in the middle of the screen. There we go. Okay, here we go.
In this lab, we will examine some network traffic using Packet Tracer's simulation mode feature. But first, let's take a look at the network diagram.
Okay, so let's talk about what we're doing first. Use simulation mode to analyze the various traffic being sent through the network. What layers of the OSI model or the TCP slash whatever it's called, what was it called? TCP slash IP. Realize the renew PC1. Release and renew PC1's IP address to generate some layer 7 traffic. Okay, so we need to, okay, let's see what he's doing for us.
There are 2 routers, R1 and R2, 2 switches, switch 1 and switch 2, and 1 server and 1 PC. The G00, G01, G02, and F01 labels indicate the network interfaces used to connect the devices. G means gigabit Ethernet.
Yes.
So these interfaces operate at a speed of 1 gigabit per second. You
That's
might also
fast.
see it written as GI or GIG, but I usually just use G. F means fast Ethernet. So these interfaces operate at 100 megabits per second. You might also see it written as FA instead of just F. Now, these two series of numbers here, 192.168.1.0/24 and 10.0.0.0/24, are the network addresses. Routers are used to connect different networks. There are two networks displayed here in this diagram. The one on the left here includes server 1, PC 1, switch 1, switch 2, and R1's G00 interface.
Yep.
They're all in a single network, or subnet, a term you will learn about soon. So that's the 192.168.1.0/24 network, and the .100
break my brain
for server
too.
1 means that its IP address is 192.168.1.100, and the .1 by R1 means that its address is 192.168.1.1. Wait for the lesson about IP addresses coming up soon for more information on this topic. The other network is 10.0.0.0/24, consisting of R1's G01 interface and
Yeah,
R2's
dude, he
G00
kinda's the
interface.
best.
Notice the .1 and .2.
I just found him the
so
other day
R1
too,
is
like when I was
10.0.0.1,
planning out
and
my
R2 is
streams and stuff.
10.0.0.2.
Actually,
Hopefully that helps you
ChatGPT is
understand a
what he
little
told
bit
me
about
him.
how to read a
Or no,
network
it's
diagram.
Claude.
Don't worry if you have no idea how IP addresses work or what that /24 next to the network addresses means. That will all be explained in a video
That's the
coming soon.
subnet.
So let's get started on today's main topic. I'm going to use Packet Tracer's simulation mode, which you can activate here in the bottom right. Now I can click through here, and you can see various network traffic being sent around. Let's take a look at some. At device switch 2 means that switch 2 is the one sending out the data. It says type STP. STP is the spanning tree protocol, a layer 2 protocol you'll learn a lot about in this course. Let's click on it and notice here the 7 layers of the OSI model, and STP has information in the bottom 2 layers. Let's look at the layer 2 header. Notice it says layer 2, IEEE 802.3 header. You might remember that IEEE 802.3 is the standard number for Ethernet, so this is an Ethernet layer 2 header. Let's look at some of the information here.
God, no, don't.
Down here it shows some information about the process, and notice here at number 2, the device encapsulates the PDU into an Ethernet frame. There's the encapsulation process I talked about in the lecture video. Let's take a look at the layer 1 info. Notice that the information is the 2 interfaces that it sends the frame out of. Information like the physical ports or interfaces on a device are layer 1 information, because it is the physical layer. Now let's look at another bit of network traffic again. This
Oh,
time,
it has it
at
broken down.
device
Okay,
R1,
I understand.
and the type is OSPF. OSPF is a layer 3 protocol. It's used
Wait, what do you do? How do you do that? How do you get to...
interfaces that it sends the frame out of. Information like the physical ports or interfaces on a device are layer 1 information, because it is the physical layer. Now let's look at another bit of network traffic again. This time, at device R1, and the type is OS.
I don't have that. I don't have OSPF. I have DTP, which honestly I've never heard of DTP. Let's keep going, see if anything happens. There we go. There we go.
OSPF. OSPF is a layer 3 protocol. It's used to discover the best paths to different networks. You'll learn a lot about it too in this course. STP only had layer 2 and layer 1 information, but OSPF has layer 3, layer 2, and layer 1 information. Notice in the layer 3 header, source IP address and destination IP address. Remember, IP addresses are layer 3 information. Next, to look at some traffic that includes information all the way up to layer 7, I will go on PC1. PC1 is using a protocol called DHCP to automatically receive an IP address.
Yes.
To generate some DHCP traffic, and DHCP is a layer 7 protocol, I'll get PC1 to release its current IP address and then renew it. When you click on a PC in Packet Tracer, you'll see this screen. Click on Desktop, then Command Prompt to access the PC's command prompt, which functions like a Windows command prompt. Type ipconfig, and you can see the current IP address here. To release the IP address, type ipconfig/release. And now you can already see a DHCP message on PC1. I'll type the next command too, to renew the IP address. It's ipconfig/renew. Now let's check one of these DHCP messages.
Hold on.
slash
Am I an idiot?
type ipconfig, and you can see the current IP address here.
Okay, I got my current IP address. Okay, cool. It's right here.
To release the IP address, type ipconfig.
What did I do? Does it need to have a space? Shit.
Slash release.
I guess so. It does. I wonder why that space matters. Whatever. Don't care. I do care, but... Okay, so now it's released. Now it has no IP address. Now I need to put IP config / renew. Okay, what did I do wrong?
And now you can already see a DHCP message on PC1. I'll type the next command too, to renew the IP address. It's ipconfig / renew.
That's what I did. Okay, I'll type it again. IP config / oh, I put 2 spaces. This one will take a second.
Now let's check one of these DHCP messages. Notice information all the way up to layer 7, except layers 5 and 6. That's because in the TCP IP model, which is the model actually in use, layers 5, 6, and 7 are all combined into a single layer called the application layer. So you're not going to see any layer 5 or layer 6 information, but you can consider it to be part of the layer 7 information. Then there is layer 4 information. If we click on it, it says the device encapsulates the PDU into a UDP segment. Remember, the layer 4 PDU is called a segment. Layer 3, layer 2, and layer 1 information is present as well. Now, if I just press the play button in the middle, it will slowly play through all of the different messages being sent through the network. That's all for this lab.
Whoa, hold on. It didn't come back with my thing. ARP. It still didn't come back with my thing. I mean, it's obviously doing what it needs to be doing, right? Interesting. That's so cool. That's so cool. Okay. I'm gonna mess with that more on my own for sure. No, definitely do not want to save. Let's get some flashcards going on here. Yeah, dude, if you're not subscribed to Jeremy's Tech Lab, you should definitely be subscribed to his Tech Lab. Absolutely phenomenal. Okay, we're going to do this. Okay. Import options. Import any learning progress. Okay, just import. "25 notes, files found, show." Okay, I think this is fine. Okay, and then we should go here. And now it's in it. And then options. Yes. Okay, good. We might come back and do some day 2 stuff too, because we didn't do all of those. But let's do some of these. Study now. And we'll have our faithful study companion here, chatbot GPT. All right. So which organization defines standards used in the local area networks? Isn't that the IEEE and then the NTEF? Something like that? IEEE, that's what it is. Okay, cool. Which organization defines standards used on the internet? Oh, that's the NTEF. Oh, IETF. I don't know why I said N. Okay, next. The IETF publishes standards and documents called... Oh, crap. I don't remember. The RFC, requests for comments. Okay, we're gonna come back to that one. In a 5-layer TCP IP model, what is layer 1? Isn't it the physical? Yep. What is layer 2? Network. Not network. Data. Local network. Data link. Okay, same thing. In layer 5 TCP IP model, what is layer 3? That one's the network. Yeah, internet network. Layer 4 is translation. Transport. Okay. And then layer 5 is application. Also called layer 7. That's a little convoluted. Oh, excuse me. I'm hungry. Okay, the IEF publishes standards. Oh, dude, we just had this one. I keep wanting to say that it's R, but no, it has to do something with comments. Local something comments. No, requests. It's the R something C. The RSC. The RFC, request for comments. Okay, we'll come back to it. In a 5-layer ITCP model, which layer sends bits as electrical, optical, or radio signals? The physical. In the 5-layer TCP IP model, which layer provides hop-to-hop delivery within the local network using MAC addresses? That's going to be a layer 2. That's going to be the data link layer. Yeah, layer 2, local network. I think that's confusing to call it local network. I understand local network switches, but I like data link layer better because its words are different than the layer that's above it that says network. In the 5-layer TCP IP model, what is layer 4? Layer 4, we got let's see here. School data link. Transport. Yeah. That's what I'm talking about. In layer 5, TCP/IP model, which layer provides end-to-end communication between hosts across networks using IP addresses and routers? Which one provides end-to-end communication? Oh, excuse me. Oh my god, dude, I'm so tired. I even went to bed early last night. I went to bed at like 10 and I woke up at like 7. Maybe that's what it is. I'm not used to getting so much sleep. Anyway, the end-to-end communication, isn't that layer 3? Isn't that networking? Yeah, the network internet layer. Yeah. Okay, the IETF publishes standards and documents called the request for comments, the RFC. Yeah. Okay, in layer 5 TCP/IP model, which layer provides end-to-end communication between application layers using port numbers? That would be the top layer, the application layer. Oh, it's the transport layer. Well, that makes sense. Okay, in the 5-layer TCP IP model, which layer includes protocols for communication between applications, creating interpreting what? Why can't I read that word? Interprinting the data. Oh, imprinting. Why was that so tough? Weird. Okay. The data. Isn't this the application layer? Yep, application layer. Okay, good. Even though I couldn't read that word, I was good. What is the name of the process in which headers and trailers are added? Isn't it the network layer? The internet layer? Oh no, what's it called? Okay. Gotta read the whole thing, dude. Okay, what is the name of the process? Not the name of the layer where it happens. It happens all the time because every time you go down, another thing gets encapsulated. So I was wrong on all levels. So it's encapsulation. And the 5-layer TCP/IP model, which layer provides end-to-end communication between applications using port numbers? That would be the transport layer. What can I say? I'm the best. All right, here we go. What is the name of the process in which the headers and the trailers are removed from a message? This is de-encapsulation. Yep. Or de-encapsulation. Wait. De-encapsulation means that it's being uncapsulated. Like it's being taken away. Encapsulated means that it's happening. So wouldn't de-encapsulation mean, like, wouldn't the negative and the positive of the word like knock each other out? And it would just be capsulation? Maybe I'm thinking too hard about it. What does PDU stand for? Fuck, dude. I hate acronyms. Oh, okay. Protocol something. I know what it is. No, I don't even know what it is. Okay. Protocol data unit. Oh, it's the chunks. It's when we add more chunks to it. I remember I visualized it. I remember seeing it in the video. An LP layer 4 PDU is called a data segment, which is UDP, or a... Man, I remember the UDP one. Segment using TCP or datagram. Oh, I combined them. I said data segment. So segment using TCP and datagram using UDP. Okay. L3 PDU is called layer 3. Is that it? Oh, they're called packets. Because each time it goes down the thing, it becomes different packets. Okay, or it gets another encapsulation. And then they're all called different things. So that one's called packets. And then, yeah, man, that one's going to take me a little bit to remember. Layer 2 PDU is called frame. It's called a frame. I don't know how I remember that. Okay, the contents of each PDU, everything encapsulated by that layer's header and trailer are called... I thought they were called frames. Oh, it's the payload. So all these words matter, and they're defined based off of where they are in the model. Okay. And every time we add a header, it changes the PDU. So we started, like, the payload is bigger than the frame, because it's everything that's encapsulated that layer's header and trailer. Okay, pretty sure that's right. The payload of a frame, LTPDU, is called... That one's called a frame. Because I remember that packet was layer 3 and then frame was layer 2. No. What? The payload of a frame. This one breaks my brain. And you go back to the video and look at it. The packet or the payload of the frame. Let's get a visual. Hassan being mad again. Okay, anyway. Nope, that wasn't it. That's
HCP to automatically.
Where is that? He talked about it somewhere around here. Okay. So when we have... Move that just a little bit. So when we have... I wish you would have put this next to it. Next to the... Oh, I guess he kind of did. So we have the data... And then we get the transport header, and then we get the internet header, and then we get the local header and trailer. And when it becomes layer 4, so layer 4 is a segment or a datagram. And then layer 3, L3 PDU is a packet. So then what's a payload? A payload, packet's payload is a segment or datagram. So then the payload of a frame. Okay. So the payload of the frame and the packet's payload is the segment and data layer. Is from layer... Well, that doesn't make any sense. Because this is saying that the payload of a frame of L2 PDU, this is the frame, and the payload of it is supposed to be the data segment or the datagram. That would just be these two. But the answer here is a packet. My thing keeps messing up because I have a monitor under my monitor.
Including the layer 4 header and the data. And at layer 2, a frame's payload is a packet.
Okay. A packet's payload is this because this is what it's adding. A frame's payload is a packet because this is what it's adding. Okay, so the payload is whatever it started with, and then it's adding whatever that layer's at. So if we were at layer 2 PDU, layer 2 PDU would be here. So its payload would be layer 3 PDU, the packet. Okay, it makes sense now. We're going to come back to that one. Which organization defines standards used in local area networks? That would be the IEEE. Yes. In the 5-layer TCP IP model, what is layer 1? Layer 1 is the physical layer. Yep. Which organization defines the standards of the internet? That would be I wanted to say in, but it's not. It's IEFT. Oh, IETF, Internet Engineering Task Force. They're a task force. In the 5-layer TCP IP model, what is layer 3? Internet. Yep. What is layer 5? Application. What is layer 2? Data link or the local network area. Yeah, layer. Yep, data link though. The payload of L2 is the frame, so that means L3 is the packet. Yep. All right. And the 5-layer TCP/IP model, which layer sends bits as electrical, optical, or radio signals? The physical? Yeah. Yeah. Okay. In layer 5 TCP/IP model, what is layer 4? In layer 5. Oh, what is layer 4? The transport layer. In the 5-layer TCP/IP model, which layer provides hop-to-hop delivery with the local network using MAC address and switches? Oh, that'd be the data link. You can always know that because MACs, switches deal with MACs. In the 5-layer TCP model, which layer includes protocols for communication between application, creating a... Oh, this is the word that I struggled with. Between applications, isn't it layer 5? Yeah. The IETF publishes standards called the request for comments. In the 5-layer TCP/IP model, which layer provides end-to-end communication between applications using port numbers? That would be the application layer. Damn it! I did that again. Transport layer. Okay. In the 5-layer TCP/IP model, which layer provides end-to-end communication between hosts? This must be my last. No, it's not. Using IP addresses and routers. Layer 3. What is the name of the process in which headers and a trailer are added to the message before transmitting it? Packet? It's adding the packet? Oh, it's encapsulation. Okay. What is the process? That's what it wants to know. Okay. The payload of a packet. The payload of a packet of LP PDU is a data segment or a datagram. Yep. Segment or datagram. There's the segment. That's the payload. And this is the new thing we're adding. Yep. The payload of a segment or datagram. Ooh. Data? Oh, look, I didn't even realize it. I'm stupid. It even says payload underneath it. Yep. In layer 5 TCP/IP model, which layer provides end-to-end communication between processes using port numbers? The transportation layer. Let's go. Okay, we're almost done. An LPPDU is called an LPPDU header and trailer. What? Oh. Okay, I misunderstood the question. Because this is that. Okay. Because it has two names. It's not called a packet. Or you know, it's called one of these two things. Okay. What is the name of the process in which headers and trailers are added? This is encapsulation. What does PDU stand for? Ah, crap. I don't remember. Protocol Data Unit. I hate acronyms. Protocol Data Unit. Okay, an LPPDU is called packets. What is the name of the process in which headers and trailers are removed from? Oh, de-encapsulation. Interaction between a layer and those above it is called. Oh. He talked about this. I don't remember. Adjacent layer interaction. That makes sense because it's adjacent from it. A lot of this stuff is kind of common sense. You just have to be thinking in the right, right space. You know what I mean? An L2 PDU is called frame. Ooh, yeah. Can't stop me now. Okay. The contents of a PDU, everything encapsulated by the layer's header trailer, is called the payload. Yes. Interaction between the layer and the equivalent layer from another device is called. Interaction between a layer and the equivalent layer on the other device. It's not the adjacent, because that's talking about the layer. It's talking about two different devices. What does it want? Same layer interaction. Because it is the same layer. It's just happening on the other side. Okay. The payload of a frame is of L2 PDU. The payload of a frame. I know what this is. Packet. Yes. You got me donuts? And a tea. Thanks, babe. Donuts, tea, the breakfast of champions. I love tea. I love hot tea. I love cold tea. I just like tea. Yeah, it's good. I've never been a coffee guy. And everyone's like, well, you haven't tried the rare coffee yet. And then they give me a coffee and they're like, what part of it don't you like? I'm like, I don't know. Maybe the part that tastes like coffee. In layer 5 TCP model, which layer provides end-to-end communication between application processes using port numbers? That's the transportation layer. Yes. The payload of packet LP of layer 3 PDU. The payload of a packet is a data segment or a datagram? Yes. What is the name of the process in which headers and trailers are added to the message? Oh, encapsulation. The payload of a segment or datagram is data. Yep, from the application layer. It's where it all starts, where it all begins, kind of. Okay. Interaction between a layer and those above it is called adjacent. Adjacent layer interaction. Last one. Interaction between a layer and the equivalent layer on another device is called same layer interaction. Yeah. Congratulations, you finished. Let's do some of these. I don't know if we'll do all of these, but this is from Friday. The IEEE standards equals 10 gigabytes. So that is going to be 802.3 AU AN. Man, I just need a chart here. Where's our buddy? Can you make me a chart of the IEEE standards of Ethernet God Dude, I hate when it does that. Of Ethernet. I am having a hard time remembering the different 802.3 X. Alright. That shouldn't take it long. Okay. See, and that's all this one is. It's nothing but this stuff. So like, what is this 802.3? Is this the AU? No, it's 10 megabytes. It's gonna be something dumb like I. Yep. There we go. There we go. This is what. Yes. This is what I want. Okay, I don't care about all the other crap that's said. I just want the chart. So 802.3 is the standard for. Okay, so I is 10 megabytes. U is 100 megabytes. Z is 1 gig. I didn't know that. AB is 1 gig. Oh, so the X and the T. So the X would be receiving, and then the T would be transmitting. Like, I just don't feel like I need to know these. Like, just these. I feel like this stuff is way more useful. Okay, blank cables are vulnerable to EMI. Oh, that's copper cables. That's Ethernet cables. Unprotected Ethernet cables. IEEE standard for 100 megabytes in the internet. That's the E. Or that's the I. U. Oh, the I was the 10. Yep. Maybe it would help me if I understood what these letters are. Does this say what it is?
I'll make this CCNA focused, instead of dumping every Ethernet-related IEEE amendment. The goal is the ones Jeremy's IT Lab CCNA commonly expects you to recognize. Yes, here is a CCNA-focused IEEE Ethernet standards chart. I'm keeping this to the ones you are most likely to see while studying Jeremy's IT Lab CCNA. Cisco describes Ethernet as the LAN family under IEEE 802.3, including 10 megabytes per second the ones I would memorize first. For CCNA, prioritize these. Memory trick. Think of it like this. Speed standards. U 100 megabits per second. AB equal to 1 Gbps copper.
Oh, dude, this
Z
is
1
gold.
Gbps fiber. ANE equal to 10 Gbps fiber. And equal to 10 Gbps copper. Power standards. AF Lig Medpo. At equal to PoA plus. BT equal to PoA plus plus.
I didn't
Feature
know that.
standards. X equal to flow control. AZ equal to energy saving. Real world example. You are looking at a switch port that says 10 over 100 1000 base T RJ45. That means the port can support 10 base T megabits per second
See, that's
Ethernet.
what I'm saying. Like, it
100
says
base
this on
TX
the
equal to
board. It
fast
doesn't
Ethernet,
say these letters.
usually 800 and 2.3U. 1000 base T equal to gigabit Ethernet over copper, usually 800 and 2.3 AB. Now if you see the big CCNA takeaway, 800 and 2.3 equal to Ethernet.
So why do we
Equal
have
to
these,
E3 tell you the
letters,
specific
though?
Ethernet technology, speed, medium, or feature.
That is not how you spell significance. Not even close. Please help me fix this. It's so bad, it can't even fix it. Google, help me fix it. I don't know why I couldn't do that. Okay, what is the significance of each letter that is after the 802.3? What do they mean and why are they there? And how do they relate to the speed and standard that it is? What? Oh, there's no E. Look, I'm being real vulnerable right now, guys. I'm not good at spelling. Never have been my whole life. I try, though. Okay, Wyatt, thanks. Fiber optic cables are connected to blank transceivers in a router. Oh, that's the small form factor thingy. Yes, small form factor pluggable, the SFP. We're still thinking. Okay, the fast Ethernet connection, a PC receives data on which pins? It's all the same except for the switch. So I think it's 3 and 6. Yeah, because if you remember last stream, we realized that the straight through and the crossover cables, the formula is any device that is not the same device going to a switch uses a straight through cable. Any device that's going to any other device, including same devices, needs a crossover cable. That's the rule. All right, what do we got?
The key correction is that the letters after 802.3 are mostly amendment labels, not hidden speed codes. I'll separate what the letters actually mean from the memory tricks that help for CCNA. 1. Simplified answer. The letters after 802.3 are basically version amendment labels. They usually do not mean anything by themselves. So, 802.3 equal to Ethernet family.
I knew that.
802.3U equal to one specific Ethernet amendment. 802.3AB equal to another specific Ethernet amendment. 802.3AF equal to another specific Ethernet amendment. The letters are there because IEEE keeps adding new Ethernet technologies over time.
So they're just amendments. So that's why it's not important. That's why this is what's important. And that's honestly, that's what's on the Switch. You don't see this on the Switch. At least I don't think so. I've never seen a Switch that has that. I've never even seen a cable that has that. Cables always have like Cat 5 or Cat 6A or whatever. Okay, let's keep going.
The key correction is that the letters after 802... The letters are there because IEEE keeps adding new Ethernet technologies over time. Each needs a unique name. The important correction is this. The speed is not hidden in the letters. The speed is usually shown in the Ethernet name, like 100 base TX, 1000 base T, or 10 G base T, is the group that develops Ethernet standards. 802, analogy? Think of 802.3 like a textbook called Ethernet, the Big Book. Every time Ethernet... The important correction is this. The speed is not hidden in the letters. The speed is usually shown in the Ethernet name, like 100 base TX, 1000 base T, or 10 G base T, is the group that develops Ethernet standards. 802, analogy? Think of 802.3 like a textbook called Ethernet, the Big Book. Every time Ethernet gets a new feature or speed, IEEE adds a new chapter. So you might have, but the chapter letter does not automatically tell you the topic. For example, Chapter U happens to be about fast Ethernet. Chapter AB happens to be about gigabit Ethernet over copper. Chapter AF happens to be about power over Ethernet. But U does not literally mean fast. AB does not literally mean gigabit. And AF does not literally mean power.
So
they are mostly labels. 3. More in-depth answer. First, break down the name. Take this. IEEE 802.3AB. Here is what each part means. So 802.3AB means the IEEE Ethernet amendment labeled AB. It does not mean A equal to something, B equal to something. That is the part that makes it confusing. Why are the letters there? IEEE started with the base Ethernet standard, 802.3. As Ethernet changed, IEEE added amendments. Early amendments used one letter, like 802.3a, 802.3a. After the single letters were used up, the labels moved into double letters. After the single letters, the labels moved into double lever. 802.3 AF, 800 Fox.
So it's just
Leaf,
going to continue.
MIT, Beschrank, talking about that actually shown. The speed is usually shown in the Ethernet physical layer name. For example, in names like 10 base T, the number tells you speed. Base means baseband signaling, and T refers to twisted pair cabling, tech target. So compare these two. The IEEE number is the standard amendment name. The base name tells you the speed and medium more clearly. CCNA focus table. Cisco switch documentation commonly lists these same mappings, including 802.
Okay, now it does make sense now why some have 2 letters and some only have 1 letter. I'm not going to lie, that does help a little bit. So anything that has 2 letters is going to be a gig or higher. Okay. We'll do a few more and then we'll call it. Come. Ooh, excuse me. Blank cables emit a faint signal outside the cable. Oh, Ethernet. UDP, unprotected Ethernet. What is the speed of a fast Ethernet connection? I think fast is 100 megabytes. Yep. When you see things like that say like fast Ethernet, like that, they're not just like gloating like, oh, it's fast. Like fast means a speed, which allows longer cables, single mode or multi-mode. Single mode allows for much longer cables. How many bits are in 1 megabit? Isn't it 1,000? No. It's a million. Yeah, I remember because in mega, millions. A blank connection allows both devices to send and receive data at the same time. Full duplex. Multi-mode fiber cables have a blank fiberglass core. Then it has a wider, so that way it can handle more things going through it. Yeah. How many pairs of wires are used in 100 base T cable? I'm pretty sure they use all 8. Ooh, they only use 4. 1,000 uses 8 then. How many bits are in 1 terabyte? Isn't it a trillion? Yeah. That's so insane, dude. The more, I don't want to get off on this because this is just like a little tangent thought. But like the more I learn about the internet, the more I learn about technology, the more I like study all this stuff, the more I understand the simulation theory. I know that has nothing to do with what we're doing, but it's just a thought that I had. How many bits are in 1 kilobit? And that's 1,000. Yeah, because kilo, I guess that means 1,000, and that's why people say K when they're talking about money, like 1K, 2K, 20K. How many pairs of wires are used in the 1,000? That one's going to be all 8. Yep. IEEE standards 802.3. So it's going to be 2 letters because it's the 10 gigabyte. So it's now we just have to understand. Well, okay, so if they started out with it being A, B, C, D, whatever, and then now it's A, B, A, E, like it's just alphabetical. So that kind of helps out a little bit, because if I know that this is 10 gigabyte, I know that anything over 1 gigabyte is going to be an A, is going to be 2 letters. And 1 gigabyte I don't know what it is, but it's probably going to be like AB, AC, something like that, right? So then 10 gigabyte Ethernet is probably going to be... I'm trying really hard not to look at it. Fuck, what is it? AE. AN. So what's the difference? Oh, because one was copper, one was not. Okay, and that's what we wanted. We wanted Ethernet. I don't understand this. If this is 10 gigabyte Ethernet, how is it mostly fiber? Whatever. I don't trust you, boy. Okay, we're gonna do like one or two more, and then we're gonna call it. 100. That's gonna be the U. Okay. In a fast Ethernet connection, a firewall transmits data on which pins? Is it gonna be 3 and 6? 1 and 2. Okay, we'll let this one be our last one. If auto MDIX is disabled, what kind of UDP cable should be used to connect two switches together? It doesn't matter. Oh, if it's disabled, we need a crossover. Yep. Okay. We're gonna call that one right there. And let's see here. Where are we? Oh yeah. No. Let's do this. Okay, so if you're here to watch some tech stuff and you want to know more about tech stuff or some of the study materials that I have, go check out my channel, Tyler Lamont. I got a bunch of videos here to kind of help you out through some of the labs from CompTIA and from Cisco's CCNA. I'm going to post some more videos. I'm working on more labs, more things like that. So if that's something that interests you, go check that stuff out. If you are here from ParaDiddlePete, go check out Tyler Lamont. But at the same time, we will be playing Gears of War tomorrow night at 8. So that's what's coming up here. So if you're interested in that stuff, there it is. Yeah. Like, follow, subscribe, all the stuff. Appreciate you guys. Thank you for sticking with me. And I will catch you guys in the next one. Oh, and don't forget, work with what you got, build what you need. I will see you either tomorrow for the gaming stream or on Wednesday for the next study stream. Later.